Good morning, everyone. I hope you guys had a wonderful spring break. I know that we are now on our third day back from spring break. Hopefully, you guys are staying motivated and continue to push through. Um, so, today we are going to start chapter 16, and that is going to be thermal energy and heat. So, we're going to start at 16.1, which is going to be thermal energy and matter. So this chapter starts off by talking about back in the 1700s how most scientists thought that heat was a fluid. Crazy to think that, but yes, they thought it was a fluid called caloric that flowed between objects. So they didn't think it was energy, they thought it was actually matter. So Count Rumford comes in and he studies the process of drilling holes in barrels of cannons. So what they do is, in order for the metal to not melt, they would put these pieces of metal in cold water. And what would happen is that the process occurred in the water so that the metal would not melt due to the heat being produced. So they thought that that water would make the metal not melt because it was colder. Well, Rumford discovered that heat was actually the result of the motion of the drill and not a form of matter. So he realized that once he was drilling into the metal, heat was being formed and transferring to the water. So some of the work done by the drill does useful work, but some of the energy is lost due to friction. Remember, if we go back in some time, we know that there's no machine that is 100% efficiency. We always know that some of the energy is going to be lost due to friction. So heat is the transfer of thermal energy from one object to another because of the temperature difference. So heat flows spontaneously from hot objects to cold objects. So in this example of the cannon, so we're drilling into the metal is warming up due to friction, and then the heat is being transferred into the cold water. Because we are going to learn in this chapter that hot is going to go to cold. So if there is something hot, it's going to flow into something cold. Temperature is going to be measure how hot or cold an object is compared to a reference point. So how cold something is, how hot something is, and we can use this and use a thermometer because we can see how hot the object is and how cold an object is. Well, temperature is related to the average kinetic energy of the particles in an object due to their random motion through space. So we're looking at, go down to the picture where it says solid and then it says cold and then hot, and then a liquid, cold and hot. As an object heats up, its particles are going to move faster on average. So when you are cold, think about it. We kind of discussed this earlier. When you're cold, you're going to want to stay near yourself and you're going to vibrate back and forth. So your kinetic energy is not going to be as much because you're not moving as fast. Well, when you're hot, you start to speed up. You think of a human. When you are hot, your temperature rises, right? So as those particles are moving, they're going to be moving quicker because they're hotter. They're going to collide more together. And then a liquid, same thing. When they are cold, the particles are not going to be moving as much. And then as they heat up, they are going to be moving quicker. They're going to be colliding together more often. And then we're going to get more kinetic energy. We talked about thermal energy is the total potential and kinetic energy of particles of an object. Thermal energy is going to depend on the mass, the temperature, and what kind of phase that matter is in. Is it a solid, is it a liquid, or is it a gas? Thermal energy, unlike temperature, is going to depend on the mass of the object. If you look into your books on page 4 75 and go to the thermal energy section, there's a great explanation. There's two different ones, and we're going to look at that right now. So if you need to, pause the video and go to that section. So it's comparing, it says thermal energy, unlike temperature, depends on the mass. So temperature doesn't really depend on the mass of the object, but when we look at thermal energy, it's going to. So it has us look at a cup of tea and then a teapot full of tea. Well, we can say that both of them are going to be the same temperature, right? Because you're going to heat them up about the same temperature. So the kinetic energy of the particles are going to be the same. If they're at the same temperature, that means that the particles are going to be moving at the same time or at the same pace. So then it goes, however, there is more thermal energy in the teapot because it contains more particles. We're comparing a cup of tea to a teapot full of tea. There's going to be more particles because there's more fluid in the teapot compared to the cup of tea. So there's going to be more thermal energy in the teapot compared to the cup because there's more particles. Yes, they are going to be moving at the same pace because they're the same temperature, but there's going to be more collisions because there's more particles. Then the next example says that thermal energy varies with temperature. So we know that thermal energy can be the mass, or it can be temperature, or it can be phase. So in this example, we're going to look at a cup of hot tea and a cup of cold tea. And in the book, it says that they are going to have the same mass. So that means that it's going to be the same amount in each cup. Well, we know that in the cold one, particles aren't going to be moving as quick, right? Because if it is cold, particles are going to slow down. But as you heat up a substance, the particles are going to move quicker. It's going to have more kinetic energy. And so that means that there is going to be more thermal energy in the hot tea compared to the cold tea. Let me explain that one more time. So in the cold tea, particles are not moving as quick. In the hot tea, they are moving quick because they are speeding up due to the increase of heat. So they're going to be bouncing back and forth more. They're going to be colliding more, which is going to give that cup of hot tea more thermal energy. All right, so we're going to look at two different definitions. I don't know. No. Okay, thermal contraction is not a definition word, but I really do want you to concentrate on thermal contraction and thermal expansion. So thermal contraction is slower particles collide less. We know that because they're not moving as quick, so they're going to not collide as often. So the pressure decreases and the object contracts. So this is called thermal contraction. Perfect example of this is if you take a balloon, we'll say we take a balloon outside and it's colder. We talked about this kind of in a couple of chapters back. If you take a balloon outside and it's cold, what's going to happen? The balloon is going to shrink. Why is it shrinking? It's because it's not going to exert as much pressure anymore because the particles are slowing down. They're not colliding into each other as much. So the balloon is going to shrink. That is an example of thermal contraction. Thermal expansion. So thermal expansion is an increase in volume of the material due to the temperature increase. Well, we know that if we took a balloon into, say, our house and it's really hot in there because our AC is broken for some reason. So we take it in there, and as you bring the balloon inside, that balloon is going to expand. Why is it going to expand? Is because the heat is going to have those particles moving more, colliding more, and it's going to put more pressure on that balloon and it's going to expand. So thermal expansion occurs when particles of the matter are moving faster or move further apart as the temperature increases. So as they are hitting, they're going to spread out. Remember, if we go back to this picture and we're looking at we'll say a solid or a liquid, you can see how the particles are moving further apart from each other when they are increasing the temperature. So they're going to spread out. It's going to put more pressure on that object. So the balloon is a perfect example how it can be thermal expansion and thermal contraction. Gases are going to expand more than liquids, and liquids are usually going to expand more than solids. So solids are going to take more time to expand compared to liquid and gases. A perfect example that we use is for thermal expansion. We talked about the balloon. You can use that example. I am perfectly okay with that. Another example is thermometers. So as the temperature increases, if we're looking at it, you stick it in your mouth and it's going to get your temperature. And as it increases, that alcohol or the mercury that's in the tube is going to expand and height is going to increase. So you put the thermometer in your mouth. It's getting your temperature, it's going to increase, right? Because your body temperature is usually going to be higher than what is in a room. So it's going to make that liquid warm up. The particles are going to start colliding more often and they're going to go further apart and it's going to cause that liquid to expand. All right, we are going to stop there for today. Tomorrow we are going to jump into our formula, and please guys, I understand these formulas are going to get a little bit difficult, but that is why I'm going to do a Zoom session with you on Friday if you have any questions about that. So today, just go over the notes that I just did, copy them down in your book, and you can call it a day. If you have any questions, please reach out to me and email me. I miss you guys so much. I'm really upset that I won't be seeing you this year, but you know that you can always come visit me next year. I'm only in the middle school hallway, so I'll see you guys soon. Miss you. Bye. I don't know how to turn this off. Oh, there it is. See you guys.